Light has always been a hell of a big deal in physics. Everyone knows that in a vacuum light travels at a constant speed c. This constant speed is unique to light and one of its defining features. But what is it that's actually travelling at this speed? Does light travel in the same way that a water wave does? Is light a wave? Or is it actually like a little marble shooting through space, a particle? In this video, you will not find out the answer. Most likely, this will just fuck with your brain, but hopefully you will get a flavour of the kind of thing that we think light is. Anyhow, let's get on with the story. This story starts properly, as with most stories in physics, with Isaac Newton. Newton proposed that light was made up of particles called corpuscles. His reason for preferring a particle model to a wave model was the fact that light was largely observed to only travel in straight lines. Waves, on the other hand, do all sorts of funky things, like diffracting around corners and bending around obstacles. Newton's theory did not account very naturally for effects like refraction, and the fact that light does actually diffract in certain situations. Nevertheless, despite the shortcomings of the particle theory, Newton's sheer fame and influence kept the theory going well past its prime. A much more convincing model of light was proposed by the Dutch physicist Christian Huygens. Ugh, I'm terrible with names. His proposal was that light was actually a wave, its oscillations perpendicular to the direction of propagation, which is a fancy way of saying it moves like this but jiggles like this. Huygens' theory was not accepted for a long time because of the popularity of the particle model, but several key experiments were carried out in the early 1800s which finally, well, not finally, but temporarily killed off the particle model. The key experiments were conducted by scientists such as Young. Young's famous double slit experiment was a key moment for the wave theory. The irony is that later the double slit experiment would be used again to suggest that light was actually a particle. Let's take a quick look at the double slit experiment. In the experiment we have one wall with two slits in it, and another wall behind it that acts as a screen. If light is a particle, you expect there to be two bands of hits on the screen behind the two slits. If light is a wave, you get some spooky magic called interference, which produces a set of bands all along the screen, called an interference pattern. Young conducted his experiment and found that, lo and behold, an interference pattern appeared on the screen behind the slits. This was a decisive victory for the wave model over the particle. Now it's time for some magic. Would it really be a physics video if I didn't get to show off some impressive equations? At this point, the wave theory had become universally accepted. The issue now is to try and work out what kind of wave light actually was. The combined work of Faraday, Maxwell, and a fair few Frenchies culminated in one of the first unified theories of physics, that is, electromagnetism. In the 1800s, people were aware of a vast range of weird electrical and magnetic effects, but didn't really know what to make of them all. Finally, after a lot of head scratching, the physicists worked out that electricity and magnetism were different sides of the same crazy coin. They were both manifestations of one superforce called electromagnetism. The actions of the force are summarised as Maxwell's equations. To put these laws briefly, we have the divergence of the electric field is the electric charge density divided by epsilon naught. The divergence of the magnetic field is always zero. The convergence of the electric field is equal to minus the rate of change of the magnetic field. And the convergence of the magnetic field is equal to... If you want to be relativistic about this, or just plain lazy, you can summarise this all as d mu f mu nu equals j nu, which seems like a ridiculously small equation capable of explaining everything from lightning storms to toasters. With the groundwork of electromagnetism in place, the nature of light was soon discovered. Now I can present you with some true mathematical wizardry. We take Maxwell's equations in a vacuum, take the convergence of the electric field, jumble this all up a bit, then we use a vector identity here, plug in Maxwell's equations again, and boom, we have an interesting looking equation for the electric field. We can find a similar equation for the magnetic field. If you have a keen eye for physics equations, you'll recognise that this is exactly the form of a wave equation. So what we found out is that electromagnetism permits the existence of a wave in the electric and magnetic field. Now let's look a bit more at the properties of these waves. To find the speed of a wave, you can look at this constant here. So for an electromagnetic wave, we get this expression for its speed. Epsilon and mu are just numbers that are determined by experiment, so we can plug this expression into a calculator to find the speed of our electromagnetic waves. Holy And there you have it. Light is an electromagnetic wave. The only question that seemingly needed addressing was the question of what is actually waving in an electromagnetic wave. In water waves we have the water waving, in sound waves we have the air waving, but what waves in a light wave? Physicists had proposed for a while that there was some spooky thing called the luminiferous ether, which sounds like a special item in Dungeons and Dragons. It is here that I leave you with a cliffhanger. It might seem like there's no way that light isn't a wave. Everything points to light being a wave, particles, schmarticles. It looks like I can safely end this story as the sun peacefully sets on the idyllic wave model. But here's the twist. The luminiferous ether doesn't exist.